Hi, welcome to MATH336. This is the first section of Chapter 5, where we're now going to start talking about linear systems of differential equations. So this is actually one of the most common ways that you'll encounter differential equations in the real world. Typically, they don't show up as just a single differential equation in terms of one function, but they'll show up as a number of differential equations involving a number of different functions. And we'll see that this is actually also important to know about for solving higher order differential equations numerically on the computer. So this first section, we're going to look at first order systems, and we'll look at an application. So let's see. So often in applications, we need to solve a system of differential equations involving more than one function. So here is a very simple example of where this shows up. We have two masses and two springs. So instead of just a single mass and a single spring, we have two of these connected together in this way. And we'll let x of t represent the displacement of the first mass from its equilibrium position. And we'll let y of t represent the displacement of the second mass from its equilibrium position. The first spring has a spring coefficient of k1, and the second spring has a spring coefficient of k2. And then we have an external force on mass 2. So the way we can think of this is perhaps there's some sort of something spinning inside here, and it's causing this mass to sort of move back and forth a little bit. So you can think of it that way. But of course, the applications of this are when you maybe have like a larger structure like a building, and then you're thinking of having a lot of different masses connected together by springs. And so you can imagine how this really scales up to having many, many functions and many equations. Okay, so let's see how we can get a system of differential equations from this two masses and two springs system. So the first thing we need to think about is what happens when spring 1 is stretched by moving this mass 1 to the right. So when it moves to the right, then it's stretched by a distance of x of t. And the resulting force is then going to be the spring coefficient times that distance. So that's what gives you the resulting force. So if x of t is positive, then this will result in a force to the left, so pulling the mass back. And if x of t is negative, then that will result in a force going in this direction as the spring tries to push. Okay, spring 2 is a little bit more complicated. So we have to ask ourselves, how much is this spring being stretched? And the answer is that, if x of t moves a little bit and y of t moves the same amount, then the spring is not stretched at all. If x of t stays put and y of t moves by itself, so x of t is 0 and y of t is moving to the right, then it'll be stretched by the amount y of t. And if y of t is 0 and x of t is pushed to the right, well, I guess we're thinking of stretching, so I guess it would be moving this way. So if x of t has a negative value, then that will stretch the spring as well. So the spring is being stretched by sort of the amount that y of t is going to the right, and then we subtract the amount of x. So after thinking a bit about it, it makes sense that it's the position of y minus the position of x that results in the amount that the spring is stretched. So if this amount is positive, then it's a stretching of the spring, and if this length here is negative, then that means we're compressing the spring. The same thing goes up here. If x of t was negative, then it's we're thinking of compressing the spring, even though I keep using the word stretched in both places. But we're sort of looking at stretching and compressing the spring. So this is the amount by which spring 2 is stretched or compressed, and that results in this amount of force. So it's the spring coefficient K2 times this distance that the spring is stretched. Okay. So then how do we write down this system of differential equations? Well, it helps to look at the forces acting on each of the masses separately. So mass 1 has the spring 1 exerting a force of K1 times x to the left. So, and then M1 has a force of K2 times y minus x to the right. Okay. And also we have for mass 2, the spring 2 is exerting a force of this amount in this direction. And then the external force is giving us a force in this direction. So the direction of these forces matters, and that will show up in the differential equation. Okay, so here it is. So we use this law of Newton that force is equal to mass times acceleration. So if we add up all the forces on mass 1, we have that, so this is going in this direction, so it's a force of negative K1x. And then this is in the positive direction, so we have plus K2 y minus x. And that is equal to mass times acceleration. So that'll be m1 times x double prime. That's the acceleration of the first mass. And then for m2, we have this force going in this direction, so that'll be a negative K2 times y minus x. And then we have the force here in the positive direction, so we get plus f of t. And then that's equal to mass times acceleration, so we have m2 times y double prime, which is the acceleration of the second mass. So now you see that we have two different differential equations. Both of them involve the functions x and y. So the differential equation that we have here for x, it involves not only x, but also y. So y is appearing in this differential equation. And in the differential equation for y, we see that y is appearing, but also x appears here as well. So we're getting, we're seeing that these two equations are coupled together. So they each depend on each other. Okay, so we have a system of two differential equations involving two functions, x of t and y of t. So in order to solve this, we have to solve them together. So that's how we solve these differential equations. To make this more concrete, suppose, for example, that m1 is equal to 2, m2 is 1, then the spring coefficient for the first spring is 4, and the spring coefficient for spring 2 is 2. And then we'll assume that the external force is this oscillating force with amplitude 40, and its period is going to be 2 pi over 3. Okay, so let's plug everything in. So we have m1 times x double prime is equal to negative k1 times x plus k2 times y minus x. And then here we have m1, which is 1, times y double prime is equal to minus k2, which is 2, times y minus x, plus the external force. Okay, so that's it. That's just plugging everything in. And we're going to look at how to solve this system of differential equations numerically using the following initial conditions. So in order to solve this numerically, we need some initial conditions, and we'll assume that the initial position and velocity of both masses is equal to 0. So we're assuming that it's just starting at rest. And it would stay at rest forever, except we do have this external force here, which is going to start oscillating back and forth. And this will set the system in motion. Okay, so the problem we have, however, is that this is a second order linear system of differential equations. And that's because it involves the derivatives, the second derivative of x and y. So that's why it's a second order system. However, in order to solve differential equations using standard numerical solvers in like MATLAB, Python, Julia, many different places you can find numerical solvers. The standard way to enter them in is to first convert it to a first order linear system. So they require that you enter the problem as a first order linear system. So this is very important. One time I had a student who took 336 with me, and a year or two later, he came to visit me in my office, and he was asking me how to solve a differential equation numerically. And this was precisely the thing that he needed to know how to do. So I really want to emphasize this this point. So this technique I'm about to show you, this is something that you will need to know in order to use numerical solvers to solve differential equations. Okay. So how does this work? So what we do is we introduce some new variables. We'll introduce 4 variables, x, u1, u2, u3, and u4. We're going to let u1 equal x. And then in order to remove, like replace the second derivative with a first derivative, we let u2 equal x prime. And then this will allow us to replace the second derivative of x, because x double prime will then be equal to u2 prime. So that'll be the first derivative of u2, and we'll be able to get rid of the second derivative. So we'll see how that works. And then we do the same for y. We let u3 equal y, and then we'll let u4 equal y prime. So then y double prime will be equal to u4 prime. So we'll have the first derivative here. Okay, so now that we have this, let's take the derivative of each of them. So if we take the derivative of u1, we get x prime, but x prime is equal to u2. So we have u1 prime is equal to u2. And as I mentioned, u2 prime is going to be equal to x double prime. u3 prime, that'll be y prime, but that's equal to u4. So we have u3 prime is equal to u4, and u4 prime is equal to y double prime. So now we can substitute everything into our original linear system. So here we had x double prime, so we replace it with u2 prime, and then we had minus 4x, so that's now u1, plus 2 times y, that's u3, minus u1, minus x, which is u1. And then we had y double prime, so that is replaced with u4 prime, is equal to minus 2 times y minus x. So that's u3 minus u1. and then our external force. Okay. So now we write down everything we need in order to get our equivalent first order linear system. So this linear system here is equivalent to the original second order linear system, but it's now a first order linear system. And what happened was the number of equations went from 2 to 4. So now we have 4 equations and we have 4 functions. We have u1, u2, u3, u4. So we get 4 functions now. So that's what happens when you go from two second order, a linear system, second order linear system with 2 equations. It will double the equations and variables. Okay, so there it is. And now this is what we need in order to enter the problem into a numerical solver. One thing we'll need is to convert the initial conditions. So we have the initial position and velocity of x are 0, and the initial position and velocity of y are 0. So this is just a straightforward translation of the initial conditions in terms of the u1 up to u4 functions. Okay, so now let's go switch over to my computer. So I'm going to switch to this. Okay. So what we're going to use today in order to, let's see, am I sharing this okay? I think so. Just make sure that I'm definitely sharing desktop too. Okay. So what we'll use today is this differential equations package that can be used to solve differential equations in Julia. So it's called differentialequations.jl. And we'll look at this tutorial on solving ordinary differential equations. So the initial problem that they look at is, it's a very simple one. It's just a single equation in terms of a single function. So let's skip past this and we'll go to the example where they solve a linear system right here. So here's how we solve a system of equations. So the example they use, it's already in first order linear system of 3 equations. And what we need to do is take this system and write it out, write a function like this, which will be each of the differential equations. So the derivative of the first variable is equal to this, the derivative of the second variable is this, and so on. So we just have to type in the derivative of each of our variables. Okay, and then after that, we specify the initial conditions like this. So we'll create a u0, and we'll just give the initial conditions. For us, it'll be 0, 0, 0, 0. And then you indicate what time you want to have the solution over. So starting from t equals 0 until some final time. And then we just say that our ODE problem is defined by this function, which gives us that defines the differential equations. And then we have our initial conditions there, and then we have this t-span, and that gives us an ODE problem. And then we simply solve the ODE problem and we'll get a solution. And after we do that, we'll be able to plot it. So in this example, they're plotting the solution using each of the 3 variables, and it gives this 3-dimensional plot called the Lorenz Attractor. Maybe you've seen this before. It's an example of a chaotic system. Okay. And there's other ways to plot the solutions as well. So we're going to be using this version in order to plot our solutions. So we'll see a plot with time versus each of our functions. Okay, so let's have a look at this. So here's my Julia prompt, and over here I have the code that we'll be running. So at the top you see, I'm just going to move the zoom thing over. At the top we have the packages that we'll be using. So we're going to be doing some plots. So I'm loading plots, and then I'm using latex strings in order to get nice math notation on the plots. And we'll be using the linear algebra package and also the differential equations package. Okay. So here's our differential equation. So if you compare this with the notes, we have that the derivative of u1 is equal to u2. The derivative of x of u2 is equal to minus 3u1 plus u3. The derivative of u3 is equal to u4. And the derivative of u4 is equal to 2u1 minus 2u3 plus 40 sine of 3t. Okay, so there's our four differential equations in terms of the four variables. And these are our initial conditions. So we have initially the system is at rest. So the position and velocity of the two masses is equal to 0. And for the t-span, I'm going to solve it from 0 until 4 pi. So this system has a period of 2 pi, we'll see. And so this, looking at from 0 to 4 pi, will allow us to see two periods of the solution. Okay, so now we just define our ODE problem. So it's this two springs function. And then we have our initial condition, u0, and our t-span. That gives us our problem. Then we'll solve it. And then after that, we're going to plot it. And here I'm going to prompt for one of 3 different plots. So we'll look at 3 different plots here. So we'll plot it with just plot the solution. We'll see what it looks like if you just say plot solution. And we'll see that that's not maybe exactly what we want. So instead, we'll want to plot x versus t. So that's 0, 1, because u1 is x. And then we want to plot t versus y. And y is u3. So we'll put a 3 there instead. So that'll give us an x plot and a y plot. And we'll plot them both on the same plot so we can see them together. Okay. So that's what these 4 plot functions are doing. And then down here, this is sort of doing the same thing, but now separating it into 2 separate plots. So I create a plot 1 for x, and then I create a plot 2 for y. And then I put those 2 on a single plot, one stacked on top of the other. So 2, 1 means 2 rows and 1 column. So they'll be on top of each other. Okay, so let's run this code. I have it in this directory that I'm in here. So I'll just need to type include twosprings example.jl. That's the name of this file. So I'll run this. Okay, so let's do the first plot. So it popped up over here. So let's bring it here. So that's what you get when you just plot the first solution, or when you just plot the solution. It gives you all 4 functions, u1, u2, u3, u4. And we know that u2 is the derivative of U1. So if you look at U1, it's the blue curve here. And you can see that when the orange curve is 0, then that's when the blue curve has a maximum or minimum. So it's easy to see that the orange curve is indeed the derivative of the blue curve. So it is giving us the slope of the tangent line of the blue curve. And in a similar way, we can see that U4 is the derivative of, or the purple line is the derivative of the green line. And again, you see the derivative is 0, and that corresponds to a maximum where the tangent line would be horizontal, so have a slope of 0. Okay, so nice picture, but what we'd like to see is just looking at x and y. So don't plot the derivatives. Well, the derivatives aren't so important for us to plot. So let's look at the second plot. Okay, so now we're just plotting x and y. X is the blue solution and y is the orange one. And we can see what's happening here, and it makes a lot of sense that initially y is affected, so the second mass is affected by the external force initially. And then after some time, that second mass is now pulling on the first mass, and now we see the first mass start to move as well. So that looks quite good. And remember, the external force has an amplitude of 40, but because of the springs and everything, we're getting amplitude here of m2, which is much less than 40, and even less for x1, or for the first mass. So we're getting a much smaller magnitude in its motion. Okay, so they're both exhibiting very interesting motion due to this external force. And we can see that the period is definitely 2 pi, so that would be 2 pi right there. And then it just repeats again and again after that. And this is because we didn't put any damping into this system, so it is just going to keep going forever. If there is damping in it, then we would see a much more complicated solution. Okay. And finally, the third way to plot this is to plot one on top of the other. So let's look at that. So there it is. So there's the third plot. There's the x solution up there, and then the y solution. All right, very powerful. Differential equations are very powerful. Very easy to model this system and write it down as a first order linear system, and then enter it in code like this. So it's very, very easy to write a function like this, and then solve it, and then plot it. So this is fantastic. Okay, so let's go back to the notes now. Okay, we're back. So yeah, please, if you're, I definitely recommend that you pause the video on the code and try to run that code yourself. So download and install Julia, add the differential equations package, and definitely have a look at that package. And once you have everything installed, then try to type that code in and run it and see if you can get the same plots and everything. Okay. So as you saw, it's very, very useful to know how to take a higher order differential equation and or system of differential equations and convert it into an equivalent system of first order differential equations. So, and this is true even if you just have a single differential equation. So it's not even a system of differential equations, but we can still write it as an equivalent system of first order differential equations. So let's see how we can do that. So remember, this is really important because this is how we're able to use numerical solvers to solve these differential equations. Okay, so let's see. We're going to let u1 be equal to x, and we'll let u2 be equal to x prime, and u3 will be equal to x double prime. And now we should be good because x triple prime, or the third derivative of x, is going to be equal to the first derivative of u3. So we will now be able to get rid of all of the higher order derivatives and replace it with just a first order derivatives. So then u1 prime is equal to x prime, but that's equal to u2. u2 prime is equal to x double prime, and that is u3. And u3 prime is going to give us x triple prime, so the third derivative. Okay, so now we can write down our system. So we'll have three equations, one for each of the derivatives of the three functions. And u1 prime, that's u2. u2 prime is u3. And u3 prime, now we look at our differential equation. So u3 prime is equal to x3, and that's equal to this and this. So we have x1 squared, that is u2 squared. And then we have plus cosine x, that's cosine u1. Okay, so there is our system. Oh, let me try that again. Get a box. There we have it. So we have a first order system of differential equations. Now it's not linear because we have these nonlinear terms here and here. So it's not a linear first order system, but it is a first order system, and we can use numerical solvers to solve this. So we would just enter this in the same way that we did before, and we'll be able to get a solution. Okay, let's look at another one. So what happens now if we have three variables? So we have an x, a y, and a z. So how do we convert this into an equivalent system, a first order linear system? Oh, sorry, a first order system. It will be linear because this one is actually linear. So, okay. So how do we do this? So we're going to let u1 equal x, u2 will be x prime, then we'll have u3 is y, u3 prime, sorry, u3 is equal to y prime, and u4 is z, and u5, oh wait, I miscounted here. Let's see, this is 4, this is 5, and this is 6, z prime. Okay. So then what do we have? So let's write this over here. So u1 prime is u2, u2 prime is x double prime, and that's up there in that first equation. So we'll replace that x double prime with u2 prime. And then u3 prime is equal to u4, and u4 prime is equal to y double prime. u5 prime is u6, and u6 prime is equal to z double prime. Okay, so now we can write out our system, first order system. So we'll have u1 prime, u2 prime, u3 prime, u4 prime, u5 prime, and u6 prime. Okay, so as you can see, we're going from 3 equations in 3 variables, and now we're going to have 6 equations in 6 variables. Okay. So, and that's because we have second derivatives here, whereas up here we had 1 equation, but we had 3 derivatives, and that gave us 3 equations. So the number of equations that you have is going to be equal to the number of equations in your original problem multiplied by whatever the highest derivative is. I suppose if you had lower derivatives in other variables, then maybe you wouldn't need all of these, right? So some of these you wouldn't need. You would only take up to the, you take the highest power of the variable minus 1, and that's how many of those you would need to add. Okay. So u1 prime, that is equal to u2. u2 prime, now that is x double prime, so we'll use that first equation. 3x minus y plus 2z. 3x minus y plus 2z. Okay, so I got those from here. So 3x minus y plus 2z. Okay, u3 prime is equal to u4. u4 prime, that's y double prime, x plus y minus 4z. X plus y minus 4z. Okay, u5 prime is equal to u6, and then u6 prime, that's z double prime, that's 5x minus y minus z. 5x minus y minus z. And there we have it. 6 equations in 6 unknowns. Okay, and it's first order, only first derivatives, no higher derivatives than that. Okay, so now we'll look at how we can solve a first order system of differential equations. So we'll look at a technique that will let us solve this by hand, but then we'll also go back to the computer, and I'll show you how you can take a system like this, and you can plot what's called the direction field for this system. And then we'll also plot the solution. I'll show you how to solve this using the differential equations package in Julia. Okay, so first of all, let's see how we can try to solve this by hand. So what we're trying to do here is go backwards. You know, we were going from a higher order equations to a first order system of equations. Now we have a first order system of equations, and we want to go back to that higher order system and then use the techniques that we have for solving higher order systems. Okay, so how can we go backwards here? So let's start with this first equation here. So x prime equals y. If I take the derivative of that, I'm going to get this, right? So x double prime is equal to y prime. And I have a formula for y prime, so I can stick that into this equation. So I get x double prime, y prime is equal to minus x. And so therefore, we have x double prime plus x is equal to 0. And there we have an equation that we know how to solve. So we can solve this either with Laplace transforms, or we can solve it using the techniques from chapter 2. Let's use Laplace transforms because we have these initial conditions. We can write those in. So notice that we have x of 0 equals 1. We also need x prime of 0. So what is x prime of 0? Well, x prime is y, and y of 0 is 0. So that means that x prime of 0 is equal to 0. So now we have the two initial conditions that we need in order to use Laplace transforms to solve this. Okay, so let's use Laplace transforms. So now we have s squared x of s minus s x of 0 minus x prime of 0. So that's the Laplace transform of x double prime. And then plus x of s, and the Laplace transform of 0 is 0. So then we get s squared plus 1 times x of s. And then we have x of 0 is 1, so this will be 1. And x prime of 0 is 0, so that goes away. So then we have minus s equals 0. And that tells us that x of s is equal to s over s squared plus 1. And actually, that's a very easy one to invert. That's already on the table of Laplace transforms. So that tells us that x of t is equal to cosine t. Okay. And what else? How do we find y? Well, y is equal to x prime. So we'll just take the derivative of x, and that will give us y. So y is equal to x prime. So that implies that y of t is equal to negative sine t. And there we have it. We have our solution, and we can check. So we need x prime equals y. So x prime equals y, yes. Y prime equals minus x. Y prime is minus x, yes. And then we have x of 0 is 1, yes. And y of 0 is 0, yes. So there's our solution. So that gives us our solution. Okay, so now we will plot the direction field and the solution in Julia. Okay, so let's go back to the computer. New share, desktop 2. Okay, move this over there. Okay, so I have this df plot code that I wrote, dfplot.jl file. I wrote a function here which will plot the direction field. It uses a function called quiver. It's called quiver because we're going to be plotting some arrows. So that's why it's called quiver. So this is a function in this plots package. And what we'll do is we'll plot different values x and y. And at each xy value, we're going to plot like a little arrow or like a vector coming from that point. And that's given by u and v. Okay. And we're also going to plot it from a to b in both x and y, and then we'll use endpoints. We'll plot endpoints, so we can sort of adjust like how many arrows we have on our plot. And this ratio is just sort of indicating like how long the arrows should be. Okay, so so I already have our differential equation entered here. So this is x prime is equal to y, and y prime is equal to negative x. So this is a function that I wrote, and it essentially will take x, y values, and it will give us the derivative of x and the derivative of y as a vector, but then it'll normalize it so that it's length 1. And I'm going to plot this from -2 to 2, and I'll use 16 in both directions, and we'll plot it. Okay, so maybe I'll just comment this other stuff out for now, so we can just look at, because this is going to add another plot here. Oops. I'll just do that. Okay, looks good. So I'm going to include not responding to me. Is it frozen? Let's see. What is going on my computer? So this Julia is doing something. Let me kill it. Let's see, did that work? Yes, killed it. Okay, good. Okay, let's launch Julia again. So it looks a little funny because the window is so small. There we go. So launch Julia. And now we're going to include this df plot package. So this is going to take a little bit of time when we're loading the plots and differential equations package. So I'm going to pause the recording. Okay. So it finished plotting, and here's the picture. So this is the direction field. So at each value of x and y, where the tail of these arrows are, we evaluate what is the derivative of x and y, and that will give us a direction. So the direction is given by y and minus x. So for example, I guess there's none of these are right at 0. So maybe let's do another plot where I make sure that there's values that are right at 0. So I'll change that to 17 and I'll run this again. Okay. So now some of these points are right at 0. So if we look at this point, say here, so this is 0, this is 1, 0. So x is 1, y is 0. So at 1, 0, when we plug that in, we get 0 minus 1 as the direction. So because it's y minus x, so we get 0 minus 1. And indeed, that arrow is pointed in the direction of 0 minus 1. So that is the direction 0 minus 1. And over here at negative 1, 0, we would get 0, 1. And so now that's pointed up. Up here, we have the point 0, 1. So that will give us the direction 1, 0, which is pointed to the right, 1, 0. And down here we have 0 minus 1, so that will give us minus 1, 0. Yeah, and that's pointed in that direction, minus 1, 0. So that's how we get these arrows. So at each point x, y in here, we plug the value x, y into the vector y minus x coming from the differential equation. And that gives us a direction, and we just plot a small arrow there, and we get what's called the direction field. And you can kind of see by sort of, looking at this direction field, it looks like everything's going in a circle. And we know from our solution that that's actually what we expect the solution to look like. When we plot x and y as t goes from 0 to whatever, we'll go from 0 to 2 pi. This will plot a circle. So let's verify that if we solve the differential equation and plot it, we do get a circle. So how do we do that? So we'll go here to this code, and I'll just uncomment this. So here we enter the first order system. So it's given by u1 is x and u2 is y. So the derivative of x is y, u2, and the derivative of y is negative x, which is u1. Our initial condition is 1, 0, and we're going to plot it we're going to solve it from 0 to 2 pi, and we'll plot it for the time equals 0 to 2 pi. So we write down our differential equation here. That's problem, and then we solve the problem, get a solution, and then we're going to plot the solution on top of the original plot using the variables 1 and 2. And so this will plot x and y. Okay, so let's run this code now. Hopefully don't have the problem again. Let's see. All right. All right, so we're going to run this code, and it's done. Oh, but the 0 did not. Did I not save it? Oh, I didn't save it. That's why. Save. Okay, saved. Plot. Still nothing. Oh, it's still working. So it's doing it. I think it's now solving the differential equation. The first time it runs, it has to compile the code. So that's why it takes a little bit longer the first time. Okay, and it's done. And there it is. So as we expected, we're getting a circle. So it's starting here at 1, 0. And then as time goes on, it's following this direction field. So it's going to go down this way. So it's going to go around the circle clockwise. right? So we're actually going around clockwise. And we can verify that by if we were to stop earlier than 2 pi, we can see like, how far did it get? So if we change this t-span from 2 pi, and we'll just change it to pi, and then we solve it again, should be faster this time. So you see it's just plotting the lower part of the circle. So it is going from this point here, and then it's following the direction field, and it's only doing half the circle because we're going from 0 to pi. Okay. So let's go back to the original one. Okay, so there it is. So there's the direction field and the solution. And we could plot other solutions as well, and they're all going to be circles. So if we started here at 2, 0, then we would get a circle that is of radius 2, centered at the origin. Okay, so let's go back to the notes. All right. Let's look at another example here. So this one's a little bit more complicated, and it's not really clear what's going on, but let's try to start with this equation here, and we'll take the derivative of this. That will give us y prime, and then actually we have a formula for y prime right here. So let's see what that gives us. So we have x double prime is equal to y prime, and then y prime is equal to 6x minus y, so we get that. And then y is equal, so let's try to get rid of all the y's, right? We have x, x, and here's a y, but how do we replace that? Well, y is equal to x prime. So let's plug that in. And now we have a differential equation which we know how to solve. There it is. So it's a nice differential equation, and we can use Laplace transforms to solve it because we have some initial conditions. The only thing is we need to know what x prime of 0 is. So what is x prime of 0? Well, x prime is equal to y. So that means x prime of 0 is equal to y of 0, which is 2. So we get x prime of 0 is equal to 2. Okay, so we have our two initial conditions that we need. So let's use Laplace transforms to solve this. So taking the Laplace transform of both sides, we get s squared times x of s minus s x of 0 minus x prime of 0 plus s x of s minus x of 0 minus 6x of s, and that is equal to 0. Okay, so collecting all the x of s terms together, we get this. And then x of 1, x0, x of 0 is 1, x prime of 0 is 2. There. So there it is. Minus, yeah, that looks good. Minus 2, minus 1. Yes, okay. So now we can solve for x of s, and we get s, let's see, that would be minus 3, so plus 3 over s squared. Oh, let's factor it. Let's factor that. So that will be s minus, or let's say plus 3 minus 2. Plus 3 minus 2, yeah. And we'll do partial fractions. Okay. So multiply both sides by the denominator, and we get this. And now we make some quick substitutions. S equals minus 3 gives us 0. Oh, this actually simplifies. I just noticed. So this is equal to this. So those actually will cancel. Okay, so we can actually stop doing this because we already have the partial fraction solution. It will be 1 over s minus 2. Okay, so therefore, x of t will be equal to e to the 2t, and y of t, so y is equal to x prime, so y of t will equal 2e to the 2t. And there's our solution. Okay. So as we saw, we're basically taking this system, first order system, and we're kind of going backwards, right? We're trying to take this first order system and determine the second order equation for x or y. And then we solve that, and then that will allow us to solve, once we get x of t, then we can easily get y of t as well. So there's our solution. Okay, so let's go over to Julia. I think that was the last example. So let's go over to Julia and see what the direction field looks like. And we'll plot this solution, see what that looks like. Okay. So share my desktop here. Okay, so we're going to look at this DF plot. Let's replace this. So let's see, x prime is equal to y, and y prime is 6x minus y. And also update this as well. So here I have x prime is equal to y. Actually, that's going to stay the same. And then it's just this one that changes. This will be equal to 6x minus y. And the initial condition is 1 and 2. And we'll plot it over, I don't know, I guess we'll have to look at the, let's look at the direction field first. So I'll just comment that out. Oops. Okay. Oh, interesting. Okay, so there's the direction field. And we're going to be starting at the point 1, 2. Oh, maybe I should make the direction field bigger, because 1, 2 is actually up at the top here. So maybe let's replace this with Let's see, 5, maybe 5. Oh, maybe we'll do, I don't like that 2.5 there. So let's do like 6. Oops. Okay, that looks nice. Okay, so we're going to be starting at the point 1, 2, which is right here. And it looks like it's just going to go kind of up. But I would also like to see like what happens before that. So I like to kind of have a nice curve that goes like this through here. So let's see, I guess we're going to want to do some negative time. So let's do like, oh, but the initial condition is 1, 0. So I guess I do have to start at 1. Not sure how to get around that. Okay, well, let's plot this. Okay, so we're solving that differential equation. And there's the plot. Oh yeah, so it's starting there. So kind of not very interesting. It just kind of goes up there like that. Don't know how we could possibly get something a little bit more interesting than that. I guess it is a straight line, isn't it? Because the solution is y is equal to 2x. And that is the line y is equal to 2x. It's a straight line. The slope is 2, and it will go through 0 here. And it'll also, yeah. Interesting. Just trying to think what other kind of solutions we could plot here. I think, so this is, which question is this? This is question number 17 in 5.1. So let's see here. Okay, so there is a picture in the solutions, and it plots like the direction field, but it also plots like a number of the other solutions that would be in here. So I'm just trying to think what other solutions might be interesting to try. I guess we could pick points that are kind of on the boundary. So I could pick some points like down here, you know, 6 minus, so at, see, minus 6, 6. Well, I guess that's not so interesting. So maybe I would start, I don't know. Yeah, maybe there would be stuff down here. So we'll start with like minus 6, 6, minus 6, 4, and so on. So maybe we could do something like this. So let's give this a try. So how would we do this? So I wanted to create like a for loop. So I'm going to do different like x 0 values. So I'm going to go from like minus 6 to 6. And that's going to go minus 6, minus 5, minus 4, and so on. And then I'll do the same thing for y naught. That will be minus 6 to 6. And then that'll be my initial condition. So it'll be x naught, y naught. Okay. And let's see. So I'm going to indent this stuff here. Oops. Oh. Okay, so this is going to add a bunch of stuff to our plots. All right, hopefully this works. Okay, I'm getting some warnings here. It's suggesting that I add the word local to these U, not, T-span, prob, and sol. But I don't think it's necessary. Let's see. So there is maybe a problem here. Let's see, we'll do plot. So that's our plot. And then down at here, I want to display the plot. I think I need to do that. Wow, okay. Oh, maybe, oh, I went overboard. I should have just done like the bottom down there and the top. That probably would have been enough. So I want to just do like, I guess I want to start, yeah, 0. It looks like if I start here, it doesn't plot anything. So I'll just start with like 0 and there. Okay, let's try this. Let me see. Maybe I will, instead of doing this, let's make a function called plot solution x naught, y naught. And I'm going to add it to the plot like that. Okay, so let's try plot solution 0 minus 6. So I guess I want to do, oh, okay, I see. Yeah, so yeah, this will be fine. So I'll do 4 y for x not equals 0 to 6. And then this will be always with y equals minus 6. So this will be x naught. Okay, this will work. And then I want to do the same thing at the top. I want to do for x naught equals minus 6 to 0. And I'm going to plot solution and this will be with y is plus 6. Okay, let's see what we get. got a new plot popped up over here. Okay, yeah, much better. And I suppose there's some other solution curves that I would also like to see in here. So like when x is 0 and y is equal to, I don't know. Let's just do everything, I guess. Yeah, let's try to do everything. So x is 0 and then y just goes from like -6 to 6. Yeah, why not? So let's do that. So we'll do for y naught equals -6 to 6, and then the plot solution. So this will be x is always 0, and then y naught. See what that looks like. Oh, I'm not getting those warnings anymore now that I put that stuff into a function. Ah, okay. Yeah, it's only going in the one direction though. Yeah, it's not going in that other direction. Yeah, not really sure how I would fix that. I guess I would have to kind of go between like x, still like y equals -, yeah. So I'd have to go between like -1 and or 1 and 2 up there. 1. Okay, let's try that. So it might be worth it. Yeah. Okay, so that would be like x is, let's see, so y is -6. So I want to do the same thing here. So I want to keep this and then make a copy of it. Oh wait. So I'll delete this one here. So I don't think I'll need that. So instead, I'm going to make a copy of that. And now on the second one, I'm just going to go like between 1 and 2. But I'll do like a step size of like 0.1. And then I'll do the same thing at the top. So at the top, I'm going to go like between -2 and 1. -2 to -1. Yeah. So I'll do from -2 steps of 0.1 to -1. Okay. Aha, so nice. Okay, so you sort of see, so kind of still missing some, of the curves in here. That was probably like too many in there. Probably I could decrease it by half. So instead of steps of 0.1, I could replace that with steps of 0.02. And that would probably look a little bit nicer. Yeah, that does look nice. So it's not quite all the solution curves that you would see in the back. In the back of the book, they have well, there's some curves that they put in here as well. So there's like curves that come in here, which would probably be coming from like in between like -3 and -2, in between like 2 and 3 here. So you'll get these other curves that go in there that would sort of add. It looks like I'm sort of empty space in here. And then finally, there's that other curve that we're getting, the one that goes through points that are on the line y equals 2x. So y equals 2x. What would that be down here when y is -6? Then that would be x is -3. I thought we did solve for that. Oh, but it's heading off in that direction. That's probably why. So it's heading off in that direction. And I think if we start at 0, I'm not sure what would happen if we started right at 0. I don't think the solution is defined there. So anyway, this is probably good enough. We sort of see all the different solutions that we're getting from this differential equation, starting with different initial conditions. So, so that's it. We'll stop there, and that has been the lecture for section 5.1. Thanks so much for watching.